We've learned that objects emit radiation because of their temperature. Thus, we call this thermal radiation. This thermal radiation is emitted differently based on how hot the object is. Here are some curves showing the thermal radiation emitted by several objects. If I asked you which one is hottest, you know that that means look for the smallest peak wavelength. We've studied and learned already that temperature is inversely proportional, or maybe we put it this way. The wavelength emitted most intensely is inversely proportional to temperature. So you look at that peak. What is the wavelength emitted most intensely? We see that value on the x-axis. A smaller peak wavelength means higher temperature. They're inversely proportional. So this graph here that I've just highlighted in green has the highest temperature. What if I showed you this type of graph? And I asked which object, A or B, is at a higher temperature? This is a trick question. You can see from the graph that they have the same peak wavelength. They both emit this x value most intensely. And so they're at the same temperature. But that might seem weird because if they're at the same temperature, why is this graph so far down? Why isn't it emitting the same amount of radiation? The answer is that this graph must have less emissivity. Maybe the emissivity is 0.7. And this graph perhaps is a perfect black body, an emissivity of 1. What we've just learned is that the intensity radiated, how much you radiate, is directly proportional to emissivity. And in fact, we will see an equation later that looks like this, where sigma is just a constant. All right, if we're going to understand what it means to be not ideal, we need to compare to the ideal case. On the left, we have black bodies. That means all of them are perfect, they're all ideal, they all have emissivity of 1. Look at the right side. We still have this red curve that looks the same as the initial picture. So what can you tell when you compare the two curves? Let's call the one on the left A and the one on the right B. Which one has a higher temperature? Which one has a higher emissivity? Take a moment, pause the video, and answer this question. The answer is that A has a higher temperature because its peak wavelength is smaller. A has a smaller lambda max, so A has a higher temperature. But which one has a higher emissivity? Compare back to the left side. This is what it looks like for the green curve to have emissivity of 1. The red curve is still ideal, but the blue curve is supposed to be higher. If you're at a higher temperature, you're supposed to emit more radiation. So we can clearly see then that the green curve has been shifted down, and it must have an emissivity of less than 1. So B has the higher emissivity. What is emissivity exactly? Well, before we launch into the definition, here's how you want to think of it conceptually. Emissivity is how close an object is to a perfect black body. This is not the definition, this is just a good conceptual way to consider it. More technically, the definition is And by the way, you can take these notes in your, record these down as you go through the video, take some notes. The technical definition of emissivity is the power emitted by a real body, so let's see that, here it is, divided by the power emitted by a black body, that's ideal, of course, all black bodies are, with the same temperature and dimensions as the real body. So it's sort of like you've got a box, this is the perfect black body, and then you have some real object, and maybe this one emits how much power? 10 watts. This one emits only 7 watts. So the emissivity would be 7 watts for the real body over 10 for the black body. This would yield an emissivity of 70%, or the way that we'll usually write it, 0.7. Let's answer this question below. Why is a highly reflective object going to have low emissivity? What do we know about reflective objects? If it's reflective, it doesn't absorb very much. That makes it a poor absorber. And a poor absorber of EM radiation, this is the crucial fact, will also be a poor emitter of EM radiation. The EMR is EM radiation. Well, why is that relevant? Because the power from the real body, the reflective body, will be much less. If it's a poor emitter, it doesn't emit much power. So this value will be much less than the power, well, we can just do one, the power of a black body, which means emissivity is less than 1. Again, the crucial fact, if you can't absorb much radiation, then you won't be able to emit much either. That's something we just have learned. And that leads directly to this conclusion. Okay, object A is at 400 Kelvin, and it emits 6 kilowatts of power. Object B is at 400 and emits electromagnetic radiation at a rate of 4 kilojoules per second, or 4 kilowatts. Same surface area, which has a higher emissivity? And the answer is object A, because the power of the real body is higher, and the ideal power of the black body is the same because they are at the same temperature and they have the same area. Okay, next one. Which has a higher emissivity? Polished aluminum or rough, worn aluminum? What do you think? Higher emissivity. Well, polished aluminum is more reflective, isn't it? So what does that mean? That means it's not as absorptive, so less absorptive. If it doesn't absorb as much, then it's also a worse emitter. So the answer should be the rough, worn aluminum. Okay. Why does a white painted chair, have a lower emissivity than an otherwise identical black chair? It's the same thing again. If you see something as white, that is all colors. If you see it as white, then it must reflect red. green, and blue are all reflected. Therefore, less is absorbed, and if you absorb less, then the power emitted by the real body is also less. Oops. This is less too. Okay. Next up, we're going to write the Stefan-Boltzmann law for a real body whose emissivity is E. We can write it like this. The intensity, that's an I. The emitted radiation has an intensity of emissivity times the Stefan-Boltzmann constant times temperature in Kelvin to the fourth power. If you want to write this using power, we simply say that intensity is power over area. And the Stefan-Boltzmann constant is in our data booklet. By the way, we have to plug in temperature in Kelvin. We use the absolute temperature. Let's skip ahead to page 27. The final thing to learn about is albedo. Albedo it's kind of like emissivity, except emissivity tells us about how much is emitted. Albedo is basically the fraction of radiation, EM radiation, that is reflected. It's sort of like the reflection percentage. The definition, though, is the total power reflected by a surface in a given time divided by the total power incident on that surface. Okay? That means if you have an object like this, and perhaps there is 10 watts per meter squared, that's the intensity of the radiation that strikes, and let's say you've got 6 watts per square meter gets absorbed, and the other 4 watts per square meter is reflected. What would be the albedo in this case? Well, the amount that's reflected is just 4 watts per meter squared, and the amount that is striking, the amount that is incident, is 10. So this gives an albedo of 0.4. And what do you notice? Consider those values. If we had something maybe a little less reflective, so now we've got 10 watts per meter squared, and maybe we only reflect 1, which means we're absorbing quite a bit more. Nothing is being transmitted through to the other side, we assume. So yeah, look at this. With a lower albedo, what will be true about the absorptive capability? Lower albedo will probably mean more absorptive. And if you're a better absorber, you have a higher emissivity. You're a better emitter as well. Okay, so we're going to use that to answer some questions like number 6, 7, 8, 9. And then, of course, we have these important equations that we want to write down. By the way, emissivity really is written sometimes with lowercase e, and sometimes we use the epsilon symbol, the same one that we have for EMF. So take a moment in your notes, you can get this down, Stefan-Boltzmann law, get those 2 versions of the law, write them both down. One is for black bodies, and the other, which is why we have this assumes that emissivity is just 1, and the other is for real bodies. We also have Wien's displacement law. Maximum wavelength, the most emitted wavelength, is inversely proportional to temperature. Definition of intensity, and the definition of emissivity, which again you probably don't need to write down because it's on the prior page. Right? Albedo, there it is as well. The final thing before we leave, whoa, there's our data booklet, but with some other equations added in. The final thing, and hey, there's the Stefan-Boltzmann constant, 5, 6, 7, 8. See that? Just 5, 6, 7, negative 8. Let's solve number 1 and 2 before we leave. Number 1 says the average solar radiation radiated or emitted by a surface is 350 watts per square meter. The planet can be treated as a black body, therefore emissivity is 1. Find the temperature. Okay, we are going to use the Stefan-Boltzmann law. And this is pretty straightforward. We know the intensity, it's 350. We know the Stefan-Boltzmann constant, 5, 6, 7, 8. 5.67 times 10 to the minus 8. So how do we isolate temperature? Well, we're going to have to divide both sides by this. Then we'll have to take the fourth root. Raise both sides to the 1/4. When you raise this to the 1/4, you multiply the exponents, and that gives t to the 1, which is what we want to solve for. So we get out our calculator. We do 350 over 5.67 raised to the power of negative 8. That's huge, and we take that and we raise it to 5.67 times 10 to the minus 8. I think I misspoke. We raise our answer to the power of 0.25, or 1/4. 280 is the absolute temperature. Number 2 is very similar, except they didn't give us the intensity. They said the power is 290, and that corresponds to an area of 1 square meter. But guess what? Intensity is power over area, and if you divide by 1, you get the same answer. This time also, the emissivity is not 1, it's 0.35. But we're going to use the same Stefan-Boltzmann law. And we plug in our values. This is going to be 290 watts per square meter. This is 0.35. That's the constant from the data booklet. You solve in the exact same way for temperature. But this time, what's it going to be? 290. Oops, there we go. 290. Doesn't appear to work. 290 over 0.35. You have to divide by 5.67 times 10 to the minus 8. And then you have to, that is equal to t to the 4th. To get rid of the t to the 4th, we take both sides and raise each side to the power of 0.25. 348, let's say, is the Kelvin temperature. Okay, you know what, just for good measure, let's take a look at 3 as well. This is pretty straightforward. We have a planet whose atmosphere has an albedo of 0.25. The intensity of solar radiation striking the atmosphere is 170, like this. There we go. And we have to find how much radiation is reflected. We simply use the albedo equation, which gives us the reflected intensity over the incident intensity. So we've got 0.25 is equal to the amount reflected. And how much is incident? That's the amount reflected over the amount that's incident. If you cross multiply, you can plug this into your calculator, but yeah, we'll go ahead and do that. I'm sure we could do this in our heads as well, perhaps. 1/4 of 170. And 42.5 is the amount that gets reflected. There we are.